Hello, Algebra 2 students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking at what will probably be the last set of notes going towards the next test. However, we still have several days before the test gets here. Of course, Monday and Tuesday are going to be days that are mostly lost to end of course testing that's going on in the building. So once we get back from that, Wednesday will likely be a review or word problem day of some kind, and then possibly next Thursday would be a target date for the test. So begin preparing yourself for that. Today we're going to look at more advanced growth and decay problems. So please copy the title. Now we've just spent the last couple of days working on growth and decay problems. Don't get particularly spooked by the title saying more advanced. It's not that it's all that more advanced, it's just that our variables might show up in different places than we have been seeing them thus far. Our objective for the day will be to learn new problem-solving skills in order to solve for any of the missing variables in growth and decay problems. Now, this is kind of a little bit something new that we haven't been doing much of here in Algebra 2 lately. We haven't learned much new math. True enough, we have talked about new equations and new types of graphs and things like that, but we have not picked up really any new problem-solving skills to go along with reading those equations or anything like that. Well, today we are going to have some new things that we're going to learn about how to work inside of an equation in order to isolate a particular variable. So let's get started. Now, as I've already said, to this point, the only challenge we have faced in growth and decay problems has been plugging in correct values in the correct places. And with both of the formulas that we have looked at, both with the incremental formula that is on the left and the continuous formula that is on the right, we have had everything that was needed in order to solve for y. In other words, we have been provided with initial amounts of something before a problem began. We have been provided with how much of an increase rate or decrease rate or constant of proportionality. We have known that value going in. We have known how much time was going to elapse between the beginning of the problem and the end of the problem. Well, those are, of course, variables. And just like any other problem, it can be any of those variables that is unknown, and we may have to solve for it. Okay, so the question that we're going to answer today is what happens if it's not the y that we are solving for? What happens if we are trying to find a, the initial value, b being some rate, x being some amount of time, or k being some constant of proportionality? What happens if it is one of those four values that is missing in the formulas? All right, so let's take a look at four different types of problems, one for each of these situations. Okay, so we'll start off here. If A is our missing variable, okay, then that is going to mean that b to the x and e to the kx are constants because b and x are both known values. So b to the x is just some number. E is just a number. If k and x are both known, then e to the kx is also just a number. They are just constants, and they can be divided away from a very easily. Okay, so let's take a look. Let's say we have a problem. A bacterial culture reveals a population of 250 cells, which have been continually expanding at a rate of 3.1% per hour. What was the population 1 day ago? Now, one of the things you're going to have to adjust to is the problems are not going to come out and tell you that they are incremental or tell you that they are continuous. It'll be up to you to read the problem and decide that for yourself. You got to get that decision correct because you got to get the formula correct. Obviously, this one is a continual expansion. The problem says so. Okay, so we will use the formula for continual growth and decay, A times e to the kx. Okay, now plugging information in, This time we have a current population, and the problem refers to something that happened in the past. So that makes y our 250, and it is the initial amount, a, that is unknown. E is a constant, so it is known. K is the constant of proportionality, which we know as 0.031 from the problem. And then X is the amount of time that has elapsed, and it is established at 1 day. Okay, now keep in mind that the expansion is in terms of hours, so we better make sure the entire problem is in terms of hours. That means our time is going to be 24. So our equation should look like this. 250 is the current amount. That equals the initial amount, which is unknown, times e to the 3.1% times 24 hours in a day. Okay. Now, A is obviously the unknown value. E is a number raised to 0.031, which is a number, times times 24, which is also a number. That means e to the 0.031 times 24 is a number, and we can put it directly into our calculator. And I'll show you how I got it here in a moment when I can find my calculator. There it is. Okay, let's take a look and see what E is doing. And of course, this is a value that is in your calculator. It is a second function on top of the natural log button. And your calculator will automatically ask you for an exponent. E requires an exponent in order to be able to finish the value that it is. We will make sure that 0.031 and 24 are both in our exponent. And there is the 2.1 that I arrived at in the problem. Okay, now the only thing left to do is to get that 2.1 away from our A, and A will be isolated. As you can see, 2.1 is multiplying times A, and the opposite of multiplication, to move it to the other side, is division. So we will divide both sides by 2.1. And 250 divided by 2.1 is 118.80. It's okay to round your decimal points once you get to the answer and round them to the hundredths place. That will be good enough. Okay, so the initial population of the bacteria was nearly 119 cells, which more than doubled in a 24-hour period. Okay. Now, if B happens to be an unknown value, this becomes a little bit more tricky. Okay, if that's the case, then what we have is we have an unknown base number that has an exponent attached to it. We are going to have to learn how to get the exponent off of the unknown base. Okay, so let's look at an example. A couple wants to turn a $5,000 investment into $10,000 in 24 months. How much interest should they look for in an account that compounds monthly? Okay, this is an incremental problem because the interest is only rolling every month. Okay, so we will make sure that we use the incremental formula, y equals a times b to the x. Plug in the values that we know. Y is the future value. We are trying to accomplish $10,000. A is the current value, which is $5,000. The interest rate is what the question is asking about. That's B. And they want to know, they want 24 months worth of time for this event to happen. So our X value is 24. Okay. Now, in order to get B by itself, then we better start moving things away from B. Now, before you can get to the exponent, that 24 that's out there, we probably better get the 5,000 off of B. We don't want B to the 24th, but we certainly do not want 5,000 of them. So that would be the first order of business. Let's take that 5,000 and divide it out of there. Okay, and obviously on the left side, 10,000 divided by 5,000 is 2. Okay, well now we are in a situation where we need B isolated, but we have 24 B's multiplying times each other. Okay, well, that's not a good thing. So we're going to need to figure out how to get the exponent off of the unknown base. Okay, so let's take a look at what kind of math is going to happen here in order to get that exponent off of our b. Okay, now there are several laws of exponents. Actually, there's 5 of them. We're looking at one of them in particular. Okay, one of them in particular is states that if you have an exponent raised to another exponent, the actual math of that is that the exponents will multiply times each other. Okay, so an exponent raised to an exponent, power to a power, is actually multiplication. So what we're going to do is we are going to use this law as a way to help us untangle what's going on in this problem. Okay, so we are here, 2 equals b to the 24th power. What we are going to do is we're going to introduce another exponent into this problem. Okay, and we're going to figure out what exponent could help us be rid of that 24. So what exponent could we raise the problem to so that 24 would become a 1? Now, keep in mind that exponents are going to multiply times other exponents. So if we raise this to a power, our new power will multiply times this existing power. So what could you multiply 24 by in order to cause that 24 to become a 1? Well, you would want to multiply by its reciprocal. If we took 24 and multiplied it by 1 over 24, then that would be a result of 24 over 24, and that is 1. Okay, so here's what the problem would look like on its next step. Okay, we're going to take both sides of the problem and we're going to raise them to the 1/24th power. And we do this to both sides of the problem, as always, because whatever you do to one side of the problem, you must also do to the other side. Now, on the right side of the problem, 24 raised to the 1/24th. That multiplies and cancels and will leave just b. So what we need to figure out is what is 2 to the 1/24th power. Okay, well, we can enter this into our calculator. 2 raised to the, and to enter a fraction, that's a division problem, 1/24th. 2 raised to the 1/24th power is 1.0293. Okay, so let's see what kind of a number I've got here. I rounded it off to the thousandth place for some reason. Doesn't matter. Okay, you could have called it 1.03 and been just fine. But at any rate, okay, there's where we're at. You move the decimal point 2 points back to the right to make it come back to a percentage, because that's what the question asks. What percent? And we have 2.9%. Okay, so there's a new skill. Let's look at something else that might happen. Let's assume for a moment that x might be the value that is missing. Okay, x is in 2 different formulas. We're going to look at it first in the periodic formula. Okay, so let's take a look at how this one works. Let's say a couple buys his and hers motorcycles for $45,000. They decide they won't keep them forever, so they're going to sell them by the time they believe they can get $30,000 back from the sale. Okay, so if the rate of depreciation is 9%, how long can they keep them? Okay, so let's take a look here. Okay, depreciation is an annual event. Okay, so we're going to use the periodic formula, y equals a times b to the x. Okay, now we're going to plug some numbers in here. I've actually got this a little bit backwards. Hold on just one moment. Okay, that's better. Had to make a quick adjustment in my notes. Had my values backwards. Current value of the the motorcycles is $45,000. Future anticipated value when they plan to sell them off is at $30,000. Now, with a depreciation rate of 9%, Okay, that means that the expected return, it would be 91%. The motorcycle would retain 91% of its value. And remember that the periodic formula, that base number, is based upon 1. 1 being the absolute, or the fact that the value will not change. So it should be bigger, going or higher numbers than 1 when we are gaining money, lower numbers than 1 when we are losing money. Okay, and of course the time is unknown for this problem. That's what it's asking. Okay, so obviously we can see that our unknown variable x is an exponent, so what we ought to do is we ought to effort to get that 0.91 by itself, since that's what x is attached to. Well, we can very easily divide the 45,000 away from 0.91 to the x. So if we divide both sides by 45,000, we get a number in the ballpark, or it's exactly 2/3, 0.667. Okay. Now, obviously, the problem is that x is an exponent. We've got to get it down from there. So what kind of math can possibly pull an exponent off of a base without wrecking the problem? Okay. Well, here we go. We have talked sporadically about the logarithmic function. Well, let's look at some of the math of what the logarithmic function can do. There are three rules that the logarithmic function abides by. One of them is going to be what we're going to do right here. If you take the logarithm of a base to an exponent, like you see on the left, log of b to the n, then what the logarithm has the power to do is to pull the exponent down out in front of itself and make it a constant. So you see the positioning of n has changed. We took the log of b to the n, and that became n times log of b. Okay, so let's see this work in the problem. Okay, so we can use this law to our advantage. Here we are, back in the problem. We have an exponent that we need to not be an exponent anymore. So if we take the logarithm of both sides of the equation, like so, and again, whatever you do to one side of the equal sign, you have to do to the other side to keep the equation balanced. On the right side, this mathematical operation will pull the x off of the exponent and place it out in front of the logarithm, just like a multiplication problem. Okay, now if you are looking at this going, what on earth is all of this log 0.667 and log 0.91? What on earth is all of this stuff? Well, let's take a look at what it is. Log of, get my calculator a little higher up in the screen, 0.667. It's a number. Okay, a logarithm is a mathematical operation. So basically, you have a number. Log of 0.667 is negative 0.1758, and so on. And over on the right side, logarithm of 0.91, it is simply a number. Okay, negative of 0.040958, and so on. So these guys are just numbers. So we can convert them in the problem to the numbers that they are. Okay, we will absolutely need the assistance of our calculator to do that. But look at what you have now. A very simple problem. We have a number that is multiplying times our variable. Okay, and all we have to do is to undo that multiplication. Divide both sides by the negative of 0.0410. Okay, and we end up with an answer of 4.3. Okay, so there you go. X is 4.3. X was time. So we're looking at 4.3 years. Okay, let's look at one more. And this would deal with the exponents in the continuous formula. And I say exponents because there's two of them up there. So we have k and x. And if one of those is missing, we're not going to do anything new. We are going to combine forces, kind of use some of the same strategies that we just talked about in order to get this accomplished. Okay, so let's take a look at an example here. Sorry for the length of the problem. Sometimes it does take a lot of words on word problems to convey this numerical information. A bone is unearthed, and the carbon-14 method of carbon dating, they call it, is going to be used to determine the age of the bone. C14 has a half-life of 5,700 years. It is determined that there should be 113 parts of C14 present, but there are only 19 parts. If the constant of proportionality is negative 0.00012, how old is the bone? Now, while you're copying that down, I'll give you a little bit of background here. The carbon dating method, basically, this applies to all living things. We have carbon-14 in our cellular structure, and as we live and breathe, the carbon-14 is converted into carbon-12, and it is constantly replenished. But as you die, obviously there is no replenishment, so the carbon-14 turns into carbon-12 and stays that way. Scientists that are able to do this, they can look at the amount of carbon-14 compared to the amount of carbon-12 that is in an object and then run it through a very similar calculation, and that tells them the age of the object. Okay, so let's take a look. Okay, this is a continuous thing. Obviously, the carbon-14 does not wait an hour and then decompose and then wait another hour and then decompose. It's happening on a continual basis. So let's take a look here. Okay, our future value of carbon-14 should be 29. Okay, I'm sorry, 19 out of the problem. Okay, that is kind of like actually that would be the current value. The initial value was determined to be 113. Okay, so looking at that, E is of course a constant. K, our constant of proportionality, is provided for us, and X, being time, is unknown. So we should be looking at a problem like that. Okay, actually the current value is 29. Okay, I'd said 19, and I believe the problem did say 19 as well. Okay, so it should be a 29. I had my problem in my equation. We're not agreeing with each other. But anyway, there you go. And you can see that you have your exponent in your variable. So once again, we're going to do the best we can to get that base that the variable is attached to. We're going to get that guy isolated. Okay, so one of the first things we should want to do would be to get that 113 off of there. Okay, we do not want the x attached to the e, but we certainly do not want 113 of them. So dividing both sides by 113, 29 becomes 0.2566. Okay, now we need to get the exponent down. Okay, and we said that one of the ways we can do that is by using the logarithm. So we're going to take the logarithm of both sides of the problem, and that will allow the exponent on the right to actually become part of the base on the right. So there I've pulled the exponent down and placed it out in front of log e. Now, keep in mind, log of 0.2566 and log of e are both just numbers. Okay, so one thing we need to pay attention to is that e, as we've already said, needs an exponent. Okay, when you push the e button on your calculator, it even automatically asks you for an exponent. On this problem, there is no more exponent of e, but remember that there's always exponents, even if one is not written, so it should be a 1. Okay, so adjusting the problem just slightly, put a 1 on the e, and log of 0.2566 on the left is negative 0.5907. Okay. Now condensing the two constants on the right, negative 0.00012 times log of e to the first is negative 0.0000521 being multiplied times our x. And of course we don't want that multiplied times our x, so we would divide it to the other side. Then x would be isolated, and we would have just discovered that our bone is 11,334 years old. Okay, so very old. Anyway, as you can see, some of these problems have a lot of steps to them, but many of the steps may be new, but they're not necessarily all that difficult. Just some new math that we've got to get accustomed to. I appreciate you taking time to get your notes taken care of, and I'll see you in class.